So how did you pause that? Are we already recording now or are we paused?
We are recording.
So the worst ever start to a video?
Well, we can trim the front off.
So,
hey, Mr. D, how are you doing?
I'm doing very well. So I'm here with my fake student who Evan Lee has mastered the art of using a stylus.
I am the stylus king, Mr.
Awesome.
Bergman here. Thermochemistry is a pretty awesome topic, I believe.
It's a pretty awesome topic.
Really cool. So, but there's a natural state. What is a natural state?
You are being very aggressive as a student. Holy cow. I wish all my kids were like that.
Hopefully that doesn't mean what I'm thinking.
No, not at all. Not at all.
Okay.
So here we go. Natural state, everything wants to have low energy. That's essentially
everything wants to have
everything.
Low energy. Like what?
Think about yourself. Do you want to be at high energy running around like crazy or sitting on your sofa?
Well, I like to do triathlon, so I always like to do
you're the
energy.
worst example I could ever use.
Yeah.
That's fantastic.
But generally what? You think about this, guys, balls, they have to go downhill, right? Because if you put the lower energy is the bottom of the hill. So if I roll a boulder from the top of a mountain, it's going to fall to the bottom of a hill. But like that work. Atoms do that too. So if I've got like water, remember it has this weird shape like Mickey Mouse, it wants to go to a lower state.
Correct. Lower state of energy. It simply means this. If you were to have your ball at the top, let's do a little point at the top there. That's your high energy state.
Yeah.
It's way easier to live at a lower state of energy. It's very hard to go the opposite way for certain. So let's say you did the backwards drawing. Put a rock at the bottom of a hill.
Right here?
Yeah. And make a hill going the other direction or going up.
Okay.
Another one right there. That's beautiful. What are the chances of you sitting there, even if you give it words of encouragement, of it ever going up that hill?
I don't think it's going to want to go up the hill because gravity's going to keep it down. So someone has to like push it up.
Correct.
But even if it gets up, it's going to like fall back down.
Yeah, it absolutely is going to want to go its lowest state. So every single atom in the universe wants to have its lowest energy always.
So that is the natural state of atoms and molecules.
Correct.
Okay, so energy then is what?
So energy, we define it as the ability to do work or to produce heat, which is a really wordish definition.
That's kind of a weird definition.
It really
I don't get that. I don't understand what that means.
Yeah, it's hard to explain, but essentially if you have the ability to do anything, either stored or not, and here's what's kind of tricky.
So basically you're saying here, if I want to do something with this boulder at the bottom of the hill, I've got to like add energy to it.
Or do work on it.
So energy and work aren't the same thing.
They absolutely are not the same.
We're going to talk about that in the next video.
Absolutely.
Okay, so let's save that for later. Okay, so thermodynamics, the first law. Are there like multiple?
There are three.
First, there must be a second.
You're an astute student. There are three of them. And the first one we call the law of conservation of energy, but it actually has an alias or AKA as the first law of thermodynamics. It's that important. So when we
conservation of energy, it means you conserve energy.
Clearly.
So like I'm cold right now, so I'm like, does that mean the same thing as I'm conserving energy?
Not at all.
It means something different, doesn't it? What does that actually mean?
Clearly it does. So when we're dealing with energy, we're talking about the fact that if you have a form of energy, you can't lose it. So if I have, if I'm moving, if I have kinetic energy, that energy can't disappear. It has to be transformed to something else, which is kind of what the definition says. Energy can either be created or destroyed, but it can change form. So in this particular example, we have someone bringing food to our helpers there. That's
I have some hot craft.
It's delightful. Thank you so much,
cheese.
Emma.
Emma was the helper.
She was delightful. So if we take a look at this diagram here, if we let go of the ball in A and it goes downwards because it's going to want to always
low energy. I knew that. I learned that. Yeah.
It's going to want to head downwards. When it hits that ball, it's going to transfer its energy.
Oh, so this is
ball.
going to hit this ball.
Correct.
Okay, it's like a collision. Okay,
clearly. And when it does, what's going to end up happening is it's going to pass its energy along towards
it whacked this one and it jumped up the hill.
Correct. So if you take a
look,
look,
it's like playing pool.
It is, and that's the example I was going to use. If you play pool and you hit your cue ball into another ball, it'll stop and the other ball will go forward. Now this ball at the bottom, it may actually still move a little bit forward,
move around or something.
But if you were to add, and this is the unfortunate thing, if you were to add up the energy that the ball has originally in A, if you scroll back up just a little bit here.
Okay, yeah.
If you have a certain amount of energy in A.
So this is 10.
So that's 10. And then when it hits the ball down below, and another ball takes over, that A ball is going to have maybe 0 now. It's stopped moving. It has no energy.
Does this one have to have 10 too?
Unfortunately, you would think it would, but because of the fact that we're in a real world, maybe that ball only has 8 or 9.
But where'd the other 2 go?
That's a great question. So we lose a lot of energy. Yeah, we lose a lot of energy due to friction. And that's probably the number one robber. Friction and heat, which we're going to talk about in a little bit, are ways that we lose
So
energy.
you really didn't lose energy; they just went somewhere else.
And that's a misnomer.
That's what conservation of energy means.
Absolutely. So if we're talking about our overall amount of energy at the very top here, if you did a little squiggle with the B, the A that we have 10, if we were to take a look at that and then compare it to the B on the second diagram, will have 8. But then if you added in the heat that's lost,
this is that lost
that
friction
lost
heat
friction
deal.
So in the end of the story, you're not going to lose energy.
So
overall.
you can never lose energy ever.
Nope.
Never, ever, never.
Energy from the beginning of time is the same as we have right now.
Weird.
Crazy stuff.
So it's this. So it's the sum. What's this? The sum total. What is this?
I don't know. That's a really good question because that's your notes. So that snuck in there on my notes a little bit here. So why don't I defer to you, student who knows a lot?
It's a constant saying that you just said it. The total amount of energy at the beginning of the universe is
fair enough.
Hasn't changed.
Yeah.
So thermodynamics, fancy word. Thermodynamics.
Well, why don't you take a shot at here, student who's very bright?
Thermo. I've had a thermal blanket before,
really
and I know that thermal blanket probably means heat. All right, so I understand the word thermal. Dynamic. Dynamo.
That means stationary, right?
No, it means motion.
Yeah.
So thermodynamics is the study of how heat moves.
Pretty straightforward, right?
It's how heat moves. So students, you should write that down. How heat moves.
Love it.
So there's 2 ways it does it. What's up with that?
So we're gonna define everything into. We love to put things into boxes. So we're gonna treat everything as either the system or the surroundings. So we are very, very excited about the system.
System and surroundings.
Yeah. So the system is essentially whatever we're working on. So if we have a reaction, that's our system.
I have hot Kraft macaroni and cheese.
That is the
system.
So
this is hot.
Yep.
So this is my system.
That is the system.
I'm gonna have some.
Yeah, it's absolutely. I'm starving now as I look at you as a fat guy. So if you take a look at that, the heat is leaving that.
I see steam coming out.
Is going to the surroundings.
So the surroundings is the room.
Correct. So in every scenario, we could go around and you could point at anything, and there's always a system in the surroundings. In fact, we can define what the system is. In physics, they have some weird ways of doing that. Mr. Bergman here teaches physics. They have some times where they define differently what the surroundings are and what the system is.
But for this case, let's just talk about. So, and here's something very important to note, guys. Here is that the steam is leaving the craft. So something always flows, always from hot to cold.
Correct.
So cold can't flow into hot. So when your mom tells you at home that when you open the window on a cold day, which never happens in Houston, I don't think.
Clearly.
I'm from Chicago. When you open the door, quit letting the cold in.
It's not a thing.
So what's actually going on? My house is getting colder when I open my door when it's 40 below in Chicago. This is
the cold hand on the warm neck principle. So if you put your cold hand on someone's neck, you are not giving them cold. You are sucking the heat off of them.
Because the heat is transferring from their hot neck to my cold hand, which makes them feel cold.
Correct. And so same sort of principle of when we are putting on blankets and whatnot, we think that the blankets aren't giving us warmth. They're just trapping in the heat that wants to leave us.
So we've got this system surroundings thing. So then there's 2 ways it can happen. There's a couple of big words. Exothermic. Now I'm a little smart. Thermic means heat. Hot. Thermic means hot. So we've got this exo word and endo. Now I'm trying to make some connections here, Mr. Dmitrovich. I remembered in biology class that they have these things with exoskeletons, and I have an endoskeleton because I'm a mammal. Is that related?
It's close. You just hit it on it. So think of X as exiting, even if you want to.
Exiting.
And if you think of endo, think of it as enduring, which is a really dumb way to say
enduring.
So entering.
Or entering, right.
So if you break it down to the word, it's really simple. Therm is, think of thermals. It's something you put on to keep warm. So heat exiting would be exothermic, and heat entering or enduring or being absorbed would be your endothermic. Incidentally, we say heat, but it could be any form of energy. Just a side note here, energy comes in different forms.
So energy in different forms. Got it. Okay.
I wish I could write that neatly with this. The reason he's doing the writing right now is because my writing is disturbingly horrible.
So there's sort of 2 graphs. For an exothermic, we'll draw the exothermic one here. Yep. It's going to look like what? You're starting lower energy.
We're going to start with our reactants, and they're going to have high energy. and then